Alright, so this is problem number 1 off of our chapter 25 homework, specifically related to electric potential. So, chapter 1, its question is, this picture of Orion Belt shows the Orion Belts constellation. Calculate the electric potential energy of the configuration if each star is replaced with a charge that is equal to 1 electron. With these given distances. So first I think it's important to note that each of these marked points is going to have a charge of negative 1.6 times 10 to the minus 19 coulombs. We'll use this a lot. I don't have space to throw all of my work on here. I'm just going to generalize it. Now essentially how this all boils down is that R1, our potential for 1, is going to have the lines going to every point that has an integer value greater than 1. So it has lines from 2 all the way to 7. And whereas like a point has like 4, it only has electric potential lines, contributor lines, going from 4 to any number greater than 4, so to 5, 6, and 7. So each of these blue lines is roughly my, potential line. If there isn't one on here, it's either represented by a black line, So really all I probably did this the long way. I kept the fundamental equation in mind that relates our potential energy to the product of our charges divided by the radius, times the permittivity constant. So for 1, there's 7 contributors, so there's going to be 21 different potentials. So for 1, we're going to have 7 different lines. So ultimately for the sum of my, I did a lot of distance calculations just using the Pythagorean theorem. So for my U total for 1, I ended up getting 1.64 times 10 to the negative 28th joules. From here it's just rinse and repeat. It's like this guy has 7 contributors, 6, 5, 4, 3, 2. U7 is 0 because there's no other greater valued numbered point that it can go to. It already has all the electric potential lines going to it. I totally realized I forgot to draw this guy. We'll just sort of rinse and repeat for this. So my U2, when I worked out all those distances, plugged it back into the formula, we get this guy. It should be 1.04 times 10 to the negative 28th joules. For U3, I got 3.93 times 10 to the negative 28th as well. And then we'll just keep moving on. For my U sub 4, I got 2.61 times 10 to the negative 28th. Awesome. And then for my U sub 5, 6.11 times 10 to the negative 29th. For my U sub 6, 3.96 times 10 to the negative 29th. Awesome. U sub 7 is 0. So essentially what this problem does, I want to come back to this guy and we'll bounce off this. We're going to take all of my potentials and then we're going to sum them up to get the total amount for this configuration. So when we do that, when we add all of these up, what I came to, is this guy. U total is going to be something close to 1.02 times 10 to the negative 27th joules. I personally did this the long way, right? I've got pages and pages of distance calculations. I want to make sure I was specific about it. Another thing that's really wonky about this problem is that the scale in the y direction, it says 1 unit up is 0.4 meters and 1 meter in the x direction is plus or minus 0.2 meters. So I kept that in mind when I was sort of graphing this all and using the Pythagorean theorem, changing y, changing x, square the sum squared. So yeah, that's pretty much it for this one. it's ultimately just like that square problem we did, except there's no symmetry. And it's a lot of tedious distance calculation and re-plugging back into the, I guess I should throw the fundamental equation on here, of u, where u is equal to k. For this one, I said kq squared because the charges are all the same. So for comparing two point charges, they won't be separate q's. So that's it for this guy. Yeah, this is what it came down to. I keep talking about those distances. Each distance that I found just gets plugged back into this r. So, yeah, there's problem 1 from chapter 25.